see it's 2 o'clock, so I'm going to let you start, and then I'm going to mute myself. Prof Peter Leach, I would like to thank you very much for hosting this mini-school series. Today, if I'm not mistaken, is the last of this series. We've had a lot of wonderful feedback. A lot of people have come and asked for the link to the YouTube. They want to watch it. So thank you very much for your time. Thanks to our attendees. And at the end, I will say thank you again. So Prof Peter, over to you. Thank you so much. All the best.
Thank you very much.
We'll chat later. Thank you.
Right. Now, the problem with all of that is nothing has happened to the screen. So I don't know whether I'm doing anything or not. Oh, I shouldn't be mute, should I? Right, well, I can't understand any of that. So, good afternoon, everyone. We now have to go and finish off this mini-series. And unfortunately, it's a mini-series from a distance. I enjoyed my time down in Stellenbosch, but I really think you should lodge a complaint with the government about warming the place up when I am down there. It's a bit cool. Now, up here on the Telsford North Coast, it's a bright blue sunny sky, no wind, well, just as gentle as ever, and the temperatures are very nice. So that means we can do a wee bit about differential equations, and preferably a lot about answering your questions, because it's in asking questions that you give me a chance to realize what is causing the problem. You see, when I give a lecture, usually, I won't say always, but usually I know what I'm talking about, and so I don't need to ask myself a question. I've already done that and answered it. But since you are listening, it really is a good idea if you go to the trouble of asking if there's something you don't understand. And I would suggest, when the occasion arises, do the asking. Don't wait until the end of the lecture, because everyone else may have fallen asleep and miss out on the very good point that you're going to make. Now, just to remind you what we've been looking at, we've been looking at ordinary differential equations, and we've been looking at their invariance under transformation. The simplest invariance, of course, or simplest transformation, I should say, is that of a point transformation. In other words, if you have x is the independent variable, y is the dependent variable, then the transformation depends upon functions which involve x and y. Now, to do this, you've got a choice. You can either use a finite transformation, in other words, x bar is a function of x and y bar is a function of x and y, and you can usually be fairly certain that what you'll obtain is a mess. Now, I'm not saying that this isn't a mess you can solve, but it's a mess, and messes are much better left to politicians rather than mathematicians. So, to overcome that problem, we use infinitesimal transformations. The infinitesimal transformation means that we only have to think of x going to epsilon c, y going to epsilon eta. Epsilon is the parameter, the infinitesimal parameter, and that means we neglect any power of epsilon above the first. Now, one of the advantages of this is that it makes the equations to be solved simpler. And that's one thing that's, well, some mathematicians like. I mean, others may not like it, I don't know. Certainly I like it. And then you can solve the equations and find the coefficient functions for the generators of symmetry. Now, what I mean by that is you have a differential operator, and it's going to generate a transformation. If you want to find the full transformation, you simply exponentiate the infinitesimal transformation, which could be an interesting exercise. But if you're lucky, usually it's not too bad. Now, the question which naturally arises is, why would you want to go and look at a transformation of a differential equation? Well, the first answer to that is, you look at the equation and you say, yuck, what on earth could I do with that? It looks complicated. It's not obvious what to do. But if you look at the symmetries of the equation, and this assumes that there are symmetries there, they don't always exist, then you can say, that symmetry as a differential operator generating a transformation could reduce the given differential equation to something simpler. And usually, if it's simpler, one can solve it without too much effort. So I'm going to give you a very simple example, of course, because complicating examples when I can't write and you can't see what I'm doing don't make any sense. But I do suggest that as I'm saying it, you write it down. If you think of an equation, let's just take y double prime equals 0. X is the independent variable. Now, if you analyze that for point symmetries, you end up with 8 of them. And you can use any of those 8 to reduce the equation from a second order equation to a first order equation. And then if you look at which symmetries are still existing, you can reduce the first order equation to a 0th order, which means an algebraic expression, and there is your answer. Now, that's a very nice idea. Naturally, there have to be catches. I mean, life was not meant to be easy. Well, that's what we're always told anyway. However, mathematicians, as you probably know because you belong to the cadre, is that the idea is to make things as simple as possible, solve it, then go back to the original setting and say, there is your answer. Now, I am a bit sorry, we have a bit of competition here, because these aeroplanes keep flying overhead, but they run away, they go off to down your way, I think. Well, that one anyway. Now, so we look at these things and we start saying, well, what is what? Does every equation have a symmetry? And the answer to that, I'm afraid, is I honestly don't know. The most useful symmetries are those which I call point symmetries. In other words, the variables in the transformation depend only upon the x and the y. But you can have more complicated transformations where the variables depend upon x, y, and y prime. Such a transformation would be a contact transformation. Now, if you're dealing with second order equations, contact transformation as far as you're ever likely to go in terms of derivatives. But for a higher order equation, it is possible that you could have something of higher order in the derivative in the coefficient functions. Now, could be. Whether or not that will be a useful piece of information depends upon what happens next. Because when you think about it, and we'll just stick to second order equations, if you have a symmetry, so C dx plus eta dy, where C and eta are functions, we'll just keep them as x and y to the point. And you want to find the simplest form of the equation. Well, you apply the symmetry requirement, which reminds me, I do hope that you looked at those papers that I mentioned to go and see what can be done in practice using computer-aided calculations, because some of these more complicated equations, the calculations can become quite hairy, lengthy, and, shall we say, prone to user error. Now, I'm not talking about you, I'm talking about me, because I've had a lot of practice at making errors. In fact, now that I come to think of it, there was a time when I did make an error, and it was such a beautiful transformation. Unfortunately, it had nothing to do with the equation under consideration. I had made a mistake. But if you use these computer-aided packages, the chances of you making a mistake are reduced. I'm not too sure about the computer itself, because sometimes the computer is faced with a choice, and computers are not known for their discernment. Well, anyway, you look at the thing and you say, okay, we can reduce the equation, we can reduce it twice to an algebraic expression, which could be complicated, but there's always the possibility that you can invert it to show that y is a certain function of x. And that is a good thing, because that means you have solved the equation. Now, of course, that does pose a little point. Why would you want to solve the equation? Well, I was hoping someone would make a suggestion. Oh, well. Silence was the stern reply. Well, suppose the differential equation describes some problem, right? Could be in physics, could be in chemistry, could be in mechanics, could be in finance, and probably a couple of other things which don't come to mind immediately, or like biology. And you get a differential equation relating things which you have identified as variables. And you say, well, okay. Well, let's take the simple example, which is not so simple, but I've mentioned it before, so by now you should be familiar with it. Suppose you have a pendulum. Now, you know a pendulum, you have a string at the bottom, you have a bob, and you flick it to one side and it goes backwards and forwards and forwards and backwards and sort of ad nauseum. Well, not quite ad nauseum because something slows it down, but to a first order approximation, it is what they call isochronous. In other words, it takes that long to go from one side to that side as it does to go from that side to that side. And such a thing is very handy. There is the story about Galileo Galilei, who was attending Mass at the cathedral in Italy, where he lived. And I guess it was the sermon going on and on a bit. And so he's looking up and he can see one of the lamps inside the church. And because there's a bit of a breeze, it was going backwards and forwards and backwards and forwards and so on. Still going backwards and forwards. And he looked at it, and then he felt his pulse to see how many pulse beats were to each of the cycles. And then he realized that the time taken for an oscillation was the same. Now, personally, I have great problems in believing this, because if I was watching this thing going backwards and forwards and forwards and backwards and so on, and I realized it was taking the same time, I would get excited. And you know what happens when you get excited? Your pulse rate goes up. So I can only conclude that Galileo was a man of very phlegmatic temperament, and so just didn't sort of worry about these things. He just looked and observed. And then he went and said, let me have a look at that. So what did he do? Well, he went home. And in those days, of course, they didn't have laboratories all over the place. Well, in a sense they did, but they were in the homes of the persons who did the work. So he constructs an apparatus and does this trick, something heavy at the bottom of the string, clamp it at the top, and let it go swinging. Now, you know, the general idea is you have it at rest, you move it to the side, and let go. Well, he tried this for different amounts of initial displacement. Not too great, actually. And he was getting the same result. Oh. What about if I change the length of the string? Then the period changed also. And there was a connection between the length of the string and the period. Wow, that's something. So he became quite excited. It was a bit unfortunate that he was a little bit on the, shall we say, impetuous side, because he managed to upset the authorities. And that had nothing to do with his pendulum. He had to consider what happens with the solar system. And in particular, in those days, it was a common belief that the Earth was the center of everything. So it's a bit egocentric. And he said, well, he used to go and observe what was going on using a pretty primitive telescope, but it was an improvement on having no telescope at all. And he looked at the orbits of the planets and of their moons, and he came to the conclusion that the Earth was not the center of the universe. So in his usual forceful way, he then said, okay, well, I better go and let everyone know. But he could have been, shall we say, a bit more diplomatic about it, because it upset the powers that be, because it was against the common belief. So he got into trouble about that, but I don't think he really ever worried too much about things like that. He must have been a man of independent means, I think. So that even if he got kicked out of his job, he still had enough to keep body and soul together. And if I remember rightly, after he had been tried by the not judicial, the other thing. Well, it was a judicial tribunal, but related to the church. And I said, you're a naughty boy. It is impossible. And so he gave up his idea publicly that the Earth revolved around the sun, and rather that the whole universe revolves around the Earth. And actually, not only around the Earth, but around man. But according to someone with acute hearing, at the comment at the end of the hearing, where he had accepted that he was wrong, he said, and still it moves. Except he didn't say it in English, he said it in Italian. But I can't remember the Italian. So that was sort of quite an event, really. Now, I think I wandered off the point somewhat. Amlin, are you still with us?
Yes,
No.
Prof.
Oh. What point was I supposed to be making?
I can't hear you properly, Prof.
Ah. Actually, I use that reason quite often, particularly when Sifi is speaking to me.
No. Actually, there is some interruption from connection.
Okay.
Can you please repeat? Thank you.
Anyway, I was is I wandered off to the story about the simple pendulum without actually getting involved in the real story, which was if you start doing differential equations and you model the motion of a simple pendulum, it's really just a 1 degree of freedom problem. And because it involves acceleration, the governing equation is of second order.
Yes.
It's of second order,
Yes, it is second order.
and it's linear,
Yes, it
which
is linear.
means that
It has 8-point symmetries.
right. And of course, the problem there is to calculate that. But I'm sure you've already done it.
Yes, yes.
You're speaking for everyone, are you?
Yes, yes, that has already been done.
Oh, good. Now, if you want to solve the equation, well, of course, actually for the pendulum, it's actually pretty easy. If you make use of the approximation that sine theta is approximately theta, because then all we have is a second order linear equation, and that's straightforward. But now, what would happen if you didn't make the approximation that sine theta is theta and tried to solve the problem theta double dot plus sine theta is equal to 0? I've got rid of all the constants. What happens there? Right. Well, I think I could agree with stand silence was the stern reply. Then you have to think about, can I do anything? And you look at it and say, sine theta is the derivative of cos theta. Theta dot, sorry, another airplane, sorry. Theta double dot is the derivative of theta dot. So if we could integrate theta double dot with respect to t, we'd be right. But now what about sine theta? We can't integrate that with respect to t. We can integrate it with respect to theta. So what would you do? You'll use plan B. You use the chain rule, and you multiply the equation by theta dot. So you now have theta dot, theta double dot, plus plus theta dot, sine theta is 0. That you can integrate. And what do you get? Oh, come on, where's all the responses? I should see a screen of waving arms. No. Very much. You get a half theta dot squared minus cos theta is equal to a constant. Now, the question is then, can you integrate that? Again, stunned silence was stern reply. Well, in that case, I should leave that to you as an exercise. See if you can integrate a half theta dot squared minus cos theta equals a constant, and integrate that to get theta as a function of time. We'll assume that you've done it because you're very smart and quick. What could you do with that result? What is a characteristic feature of a pendulum? It puts up with a very uniform existence. It goes boing, 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 boing. It's periodic. So if you solve it, you should get theta is a periodic function of time. And when you look at the solution, it should tell you what the period is. And so you would know something. We'd also know that the parameters in the original equation do have some influence on the period. What would be the chief influence? Right, let me start you off with a possibility. How about the price of eggs in China? No one's buying that. I think that you are very much given to science. Are you Cartesians? Well, for example, suppose you wanted to go and have people working for you and working for a certain period of time so that you could pay them for a certain period of time. But if you had a measurement of time upon which you could rely, then your problem about how long they've been working would be solved. So you take your pendulum, set it up, get it going, and sit there counting away. And then when the end of the day comes and the workmen are ready to go off home, you say, oh, well, there were so many, I won't go into the number because we don't know the actual period of the pendulum. And, oh, well, you worked for that long, at such and such a rate, here's what you get paid. Of course, they will say, thanks, boss. It's only half of what we expected. But that's got nothing to do with the pendulum. So the idea was to turn the pendulum into an accurate recorder of time. Well, that was done. And even still, these days, you see, even in homes, people have pendulum clocks. And of course, some of the great clocks in cities are also pendulum clocks. In fact, some of the great clocks in cities are what you might call architectural marvels. They can do all sorts of things. I mean, there's one somewhere in Italy where every hour, someone, as a statue, I mean, comes out and blows a trumpet to announce the hour. How on earth did that happen? Well, I leave that to you as an exercise on Wikipedia, I think it's called, or Google. But some of those clocks are actually quite fantastic. The ones I know of are in Europe, but I expect that in other countries, other parts of the world, you'll find something along those lines. Elaborate time measuring instruments. Okay, we wandered off the point as usual. If you think of the differential equation, theta double dot plus sine theta equals 0. Remember, I've incorporated the constants into the time. And you decide, how many symmetries does it have? So what do you do? Not good enough. What do you do? Remember, I told you, you can calculate the symmetries either offhand or using a package, and that even in Mathematica, they have a package for doing just that. So you can go and put the equation in, push the button, and find out how many symmetries. Now the question would be, how many symmetries do you expect to get? Right, now, just to remind you, if you had the simple second order equation, theta double dot plus theta equals 0, you'll get 8-point symmetries. Question is, how many will you get for theta double dot plus sine theta equals 0? Now you can do the calculation by hand, or if you're sensible, you go and look at one of the packages available and push a button and say, oh, that's interesting. Now, why will it be interesting? Because there will not be 8 symmetries. When I talk about 8 symmetries, I do mean point symmetries. So, if we have that, what happened to the other ones? Ponder that. And you can always write me an email with your suggestion to an answer. Now, I just realized that I've been talking about second order equations and point symmetries non-stop. And when I talk about second order equations, I've actually been talking about scalar equations, not systems. You can apply these ideas to calculate symmetry to higher order equations, to systems of equations, and moreover, to partial differential equations. Now, in the case of partial differential equations, sometimes you have a choice as to what use can you put the symmetries of the equation to. And one of them, of course, is to reduce the order of the equation. But an alternative, an attractive alternative, is to change the partial differential equation into an ordinary differential equation. Now, suppose you have your PDE has the variables t and x. So you have partials with respect to t, partials with respect to x, and maybe even day 2, day t, day x. How would you make that just one variable? Oh dear. Why is there so much reluctance to make a comment? No, just wait around. I'm distracted. No, it doesn't say much for me. Okay, well, there are a couple of chats there, but they weren't questions. Oh, no, I forgot the question. Yes. Well, come along, make a suggestion. Say something. Yeah.
Prof, can I ask a question?
You're most welcome to.
So the when you mentioned about the simple harmonic oscillator, and we have this there are total of 8 point symmetries for the simple harmonic oscillator. Now what can we say about the first integrals? So can we say something with respect to its first integrals or anything? Like this may have a equation.
That's a good question. So what you're saying is you have a differential equation. You manage to work out one or more first integrals, and you want to know what symmetries are associated with the particular first integrals. Am I right?
Yes. Yes. Yes.
Well, you just go and calculate the symmetries.
Okay. So, is there any standard rule like a linearizable second order equation with maximal symmetry can have this many first integrals? Is there any rule, anything like that, or?
Well, you realize that if we're talking, stick to a second order equation, okay?
Yes.
And you're saying it's linearizable.
Yes.
So there's a second order, it could have two first integrals.
It will have only 2 first integrals.
Oh, I see what you mean. Now, you can have a whole army of them, but each of those integrals will be a function of what you might call the fundamental first integrals. In other words, there's not
Yes.
new information. It's just written down in a different way to confuse the audience.
So it will have, okay, so for a maximal second order equation, only 2 first integrals, and we can, those 2 first integral are function of certain fundamental first integrals. Is that right?
Yes. No, sorry. You have 2 fundamental first integrals, and
Okay,
any
okay.
other first integral will be a function of those 2.
So in that case, we can have infinitely many first integrals.
Oh, yes.
Okay, so for a linearizable second order equation with maximal symmetry, we can have, like I think for any maxima equation with maximal symmetry, whether it is second order or third order, infinitely many first integrals.
Yes, but Amlin, remember, not independent.
They could be dependent first integrals. Right.
Now, for example, if you take a third order equation,
Yes.
third order equation could have 3 independent first integrals.
Yes.
And if you take any combination of those three, you'll still have a first integral.
Okay. So infinitely many. So we don't say anything about dependent or independent. That can possibilities that there can be infinitely many first integrals. So you just say that.
That's right.
And just one more question is that so here when we find the point symmetries and everything, it is with respect to the canonical in the xy plane. Canonical. Sorry, what is this? Cartesian plane. And
Amber, if it's the first integral,
no. I'm just saying that the second order equation, the simple
Mhm.
harmonic. So we have x and y, these two variables,
yeah,
Cartesian coordinates. So if we can we write this equation in terms of, if when we write this equation in terms of Lagrangian coordinates or in terms of uh, let's say Hamiltonian coordinates, can we expect some more symmetries or what can we expect? That is
no,
what is my
no more
question.
symmetry.
Sorry?
So on the other hand, if you come here, you can expect more monkeys by the second. Oh dear. A monkey just jumped into one of Sylvia's flower boxes. Just make sure I don't forget to make it look like it's. It seems to be monkey day today. You know what they do? They travel around the estate and they visit different parts at different times to go and lull the local people into a false sense of security so that they can do their damage. All right. Now, getting back to your question, you can have whichever integrals you like. You can say, all right, two integrals are fundamental simply because they are the simplest expressions possible. But that doesn't mean you can have a complicated looking integral, and you cannot use that as one of your fundamental integrals. I mean, it may seem a bit daft to do it, but you can do it. Just as long as you pick on two which are independent and of course have the property that the total derivative when the differential equation is taken into account is a very comfortable zero. Right. You okay now?
Yes.
Okay. I'm just wondering whether it's going home time for the monkeys. Do you have monkeys where you are?
Yes. I got it. Thank you, Prof.
Oh, all right. Yes, I think what it is, there has been a recent outcrop of new monkeys. And they're very busy exploring the area to go and see possibilities of mischief. Anyway, we should go back to the point, which is to do with symmetry. And Amlin, you're allowed to make a comment.
Yes, Prof. That's fine. I understood this.
No, all right. Right, well, I think that must be getting close to wind-up time, since we have this funny business of starting on the hour. The monkeys are really getting quite sort of agitated. Yeah. You know what happens to monkeys when they become agitated? Yeah, well, that's probably just as well. 2, 3, 4, 5, 6. Oh boy. It's really quite amusing. So, yes, I'm waiting patiently.
Prof, hi, Rena here. Sorry, I was out trying to go see what the queue looks like to go and vote. I just want to tell you, Prof, that I've given permission to our attendees here today to talk. So if people have questions, please, guys, the time is now to please raise your questions. Amlan, thank you for your questions. Masihlumi Zide, I see you here. Do you have a question? I'm trying to see who else. If anybody has questions, guys, this is your opportunity to ask Prof. Please go ahead.
But Renee, I'd say there are two possibilities.
Yes, tell me.
One is that exposition was so brilliant, the questions were superfluous. The
Yes.
other is no one understood the word.
Well, I definitely know which one it is. And Amlan, I'm sure you can agree with me which one it is. Okay, Masihlumi Zide has just said no, thank you. At the moment, Masihlumi doesn't have a question. Does anybody else have a question? Otherwise, we can, I just want to going once, going twice. Otherwise, we can thank Prof.
Yeah. Now, Renee, if anyone does have a question, they can always send an email to me.
Yes, perfect. Perfect.
Yeah.
Okay, I think I'm going to type in the chat. Is that okay if I type Prof's email address in the chat so that if anybody has got a question, they can, okay, is that in order with Prof? If I put your email address in the chat, if somebody has got a question?
No, I saw some pink, no, yellow hands wandering up the screen.
Yeah, that's definitely people that were thanking you for your, yeah, for the presentation. Thank you very much, Prof. Thank you for your time. Thank you to our attendees. There are some people that have been here every of these sessions. Also, there were people in Stellenbosch in person. So thank you for those people. Today is a public holiday in South Africa, so we only have this online today. Amlan also thanks for your questions, but in particularly thanks to Prof Peter. He was here in Stellenbosch for almost a month, and we had a colloquium. Yeah, we had lots of interaction. So thank you very much. Thank you to everybody. And remember, this will, as from tomorrow, be on our YouTube channel. So if you have any colleagues or you want to rewatch any of these sessions until now, please feel free to go and watch it on our YouTube channel. So with that, I think I want to thank everybody. Prof Peter, thank you so much.
Thank you, Renee.
It was lovely having you here.
Thank you.
Thank you. It was a
Allowed
pleasure.
to come again?
What did you say, Prof?
Am I allowed to come again?
Are you allowed to?
Come again.
Yes, please. It will be absolutely lovely. I think we need to start planning.
Yeah, I think actually there is room for a little bit more.
Yeah, no, this is absolutely wonderful. And definitely, this mini school you saw now today, this works absolutely lovely with this, wherever you're sitting with the monkeys. I saw on the left-hand side on the hedge, there were some monkeys. So, no, this worked fantastically. Thank you very much, Prof. Thank you to all our attendees. I think then we can stop here. So I'd like to thank everybody and have a wonderful day. And thanks for being here. Thank you, Prof.
Thank you, Renee, for being so sweet, kind, and gentle.
You are most welcome. Would love to see you again. Take care, everybody. Have a good day. And for those in South Africa, please go and vote if you haven't already. Thank you. Bye-bye, everyone.
Bye.
Bye-bye.